Howdy. This video is on the Henderson-Hasselbach equation. The Henderson-Hasselbach equation gives us an easy way to calculate the pH of a solution that contains a weak acid and its conjugate base. The Henderson-Hasselbach equation can help us select a buffer solution or an acid-base indicator. The Henderson-Hasselbach equation can help us better understand acid-base solutions. So after watching this video, you should be able to derive the Henderson-Hasselbach equation and know what approximations to use. And you should use the Henderson-Hasselbach equation to calculate the pH of a solution of weak acid plus its conjugate base. And so if you're asked about the hydrogen ion, hydroxide ion, pH or pOH or something, the first thing to figure out is what are you dealing with. If it's a strong acid or a strong base, those completely disassociate, so you do not need to do an equilibrium problem. If it's a weak acid or a weak base, you have to do an equilibrium problem, and so you have to determine the equilibrium reaction involved, find the equilibrium constant, and then do the equilibrium problem, typically using a nice table. And so, for example, we could be asked, what is the pH of a 0.01 molar solution of acetic acid? And so the first question is acetic acid a strong acid, a weak acid, strong base, a weak base? Well, the COOH means it's organic acid, and so it would correspond to a weak acid. And then what is the equilibrium reaction that we're going to have to solve? And so for an acid, you could have the acid breaking apart into hydrogen ions plus anion, or we could have the acid plus water forming hydronium ion plus the anion. And so these two reactions are completely equivalent. Pure liquids and pure solids and pure liquids do not appear in equilibrium expression, so we don't have to worry about that. The hydronium ion and the hydrogen ion are exactly the same. They're equivalent, so that's okay. And so we could use either of those two equations. They are exactly equivalent. So if we use the top one, now the Ka for acetic acid is 1.8 times 10 to the minus 5. Now we can make the table. So initial change equilibrium. So initially we have 0.01 molar acetic acid, 0 hydronium ion, 0 acetate ion. When X of this dissolves, we'll get X of that, and then equilibrium is initial plus the change. Now, what approximation can we make? And so equilibrium constant is products over reactants, and so if your K is really small, it means you're going to have mostly reactants at equilibrium. And so most likely, X is going to be negligible compared to 0.01. Now we can write down our equilibrium expression. Products over reactants, coefficients become exponents. Pure solids, pure liquids do not appear. And so X times X gives us X squared divided by 0.01. That equals our K. So multiply both sides by 0.01. Take the square root, and we get X equals 4.24 times 10 minus 4. And so our approximation was good. That is a lot smaller than 0.01. And so the hydronium ion concentration is equal to 4.24 times 10 minus 4 at equilibrium. And from that, we can also calculate the pH. Now, another question we could be asked is, what is the pH of a solution that has acetic acid of 0.7 and acetate ion of 0.6? And again, it gives us our Ka of 1.8 times 10 minus 5. And so again, we can make our table initial change equilibrium. This time we have initial concentration of acetic acid, initial concentration of acetate ion, initial concentration of hydrogen ion is 0. And so when X of this reacts, we'll get X of that, X of that. Equilibrium is initial plus the change. And so we're treating this like an equilibrium problem. Now, our K is really small, and so our X should be negligible compared to 0.7. Now, if it's negligible compared to 0.7, it's probably also negligible compared to 0.6. And so we can use the approximation that X is negligible compared to 0.6 and 0.7. And so it gives us these concentrations at equilibrium. Now, it's kind of interesting. So we have our Ka is equal to products over reactants, coefficients become exponents, pure solids, pure liquids do not appear. And so this is our expression for our Ka. Now, if we multiply both sides by acetic acid concentration and divide both sides by the acetate ion concentration, we get the hydrogen ion concentration is equal to acetic acid concentration divided by acetate ion times our Ka. Now, we can actually calculate the hydrogen ion concentration straightforward just this way. Now notice for our acid concentration or base concentration, those are initial concentrations because we assumed X was negligible compared to those initial concentrations. And so this is actually a fairly general equation. And so if we plug in the concentrations, we get the hydrogen ion concentration is 2.1 times 10 minus 5. And so our approximation was good. This is a lot smaller than 0.6 and 0.7. Now if we take the minus log of that, we get a pH of 4.68. And so if we look at this equation, again, the general form says the hydrogen ion concentration is equal to initial, that's what that little subscript 0 means, initial concentration of the acid divided by initial concentration of the base times the Ka. So notice that the hydrogen concentration depends on Ka and the ratio of the initial concentrations of acid to base. Now we can play with this equation a little bit. If we take the negative log of both sides, that would give us negative log of hydrogen concentration is pH, negative log of Ka is pKa, and then we have minus log of the acid over base. Now if we want to change that negative sign to a positive sign, all we have to do is flip that fraction. And so that gives us the Henderson-Hasselbach equation that says the pH is equal to pKa plus the log of the concentration of the base over the concentration of acid. You have to remember that these are actually the initial concentration of base over the acid, and this is just for acid-base conjugate pair. And so notice that the pH is determined mainly by the pKa of the acid, and then you can adjust the pH by adjusting the ratio of acid to conjugate base. And again, this is only suitable when you have just a weak acid and a conjugate base. And so using this equation, we can calculate the ratio of concentrations given the pH. We can calculate the pH given the concentrations. We can also determine the best Ka for a buffer with a specific pH, or we can also determine the best Ka for acid-base indicator if we know at what pH titration will go through the endpoint. And so initially I mentioned that, if you have a strong acid or strong base, you do not need to do an equilibrium problem because they completely disassociate. For weak acids or weak bases, you do have to do an equilibrium problem. Now, if you have a mixture of a weak acid and its conjugate base, you can actually just use the Henderson-Hasselbach equation. So what is the pH of your blood if the ratio of bicarbonate ion HCO3- to carbonic acid is 20:1? And so the Ka of carbonic acid is 4.5 times 10⁻⁷, which means the pKa, remember P of x equals minus log of x, so pKa equals minus log of the Ka, and so that gives us a pKa of 6.35. Now we can use the Henderson-Hasselbach equation. So we found our pKa was 6.35 log of base over acid, so 6.35 divided plus the log of 20, and so that gives us a pH of 7.65. So metabolic processes normally maintain the pH of a human blood between 7.35 and 7.45. The chemistry is a little bit more complex than was presented here. What is the pH of a solution that contains 0.5 moles of HF and 1 mole of sodium fluoride? And so you have to remember sodium fluoride is going to dissociate into sodium ions and fluoride ions. Now sodium ions are neither acidic or basic. They are just neutral, so we can just ignore the sodium ions. Remember, conjugate bases of strong acids are neutral. Alkaline metal ions and alkaline earth ions are also neutral. So sodium is alkaline metal ion, so it's going to be neutral, so we can just forget about it. Also notice that when you look at the Henderson-Hasselbach equation, you have concentration of the base over the acid. Now the concentration is moles over liters. Now those liters are going to cancel, and so you could just do moles of base over moles of acid. So when you're doing the Henderson-Hasselbach equation, you can do the concentration of the base over the acid, or you can do mole base over moles of acid. Those two are completely equivalent. And so we had that the Ka of HF is 6.3 times 10⁻⁴. That gives us a pKa of 3.2. And so for Henderson-Hasselbach equation, we have pH equals pKa plus log base over acid. And again, we can just use moles here. And we're given the moles of sodium fluoride is 1. Again, sodium is neutral, so we don't worry about it. And so we have 1 mole of fluoride ion, 5 moles of HF, and so that gives us a pH of 2.5. And so again, if you're given a weak acid and conjugate base mixture, you can use the Henderson-Hasselbach equation. Remember, Henderson-Hasselbach is only appropriate when you have a weak acid and conjugate base. Remember, to go from the acid to the base, we just remove a hydrogen ion, and so both the number of hydrogens and the charge changes. To go from the base to the conjugate acid, we add a hydrogen ion, And so again, number of hydrogens change and also the charge changes. And this also shows us that something can behave like an acid in one reaction and can behave like a base in another reaction. So remember, in Bronsted-Lowry theory and Lewis theory, you're looking at how something is behaving in a reaction. And so in one reaction, water could behave like an acid. In another reaction, water can behave like a base. And so all buffers and indicators are composed of weak acid conjugate base pair. And so the Henderson-Hasselbach equation is very important for buffers and acid-base indicators. So a Henderson-Hasselbach equation, pH equals pKa plus log concentration of base over acid. Again, you can also use the number of moles of base over moles of acid. It's only appropriate when you have a weak acid and conjugate base. You can use it to calculate the ratio of the concentrations given the pH, or the ratio of the moles. You can use it to calculate the pH given the concentrations, and you can use it to determine the best Ka for a buffer at a specific pH, or even to help you choose what is the best acid-base indicator. Notice that tells you that the pH is determined largely by the pKa of the acid and then adjusted by the ratio of acid to base. And I should also mention that if the concentration of the base equals the concentration of acid, that fraction would equal 1. Log of 1 is 0. And so if your concentration of base equals concentration of acid, then the pH equals the pKa. I hope that was helpful.